Hello students, welcome to my class. Today I am going to discuss few questions related to coordination compounds. As I have told you, this is one of the most important chapter related to your syllabus. So, let us move to the question answer round. So, look at my first question, what is given here, check it out, wait for a moment. Now, I am moving here, I am starting from here, that is the answer of this question. What is the question? Discuss the nature of bonding in metal carbonyls. Do you remember the example of metal carbonyls? NiCO4, FeCO5, CrCO6, etc. These are the metal carbonyls, organometallic compounds, that is there is a linkage between metal and directly carbon. Clear to you? Yes. What is the bonding here in this case? Listen. What is? That is, suppose this is a metal, clear? Wait for a moment, let me draw once. Clear? This one is metal and this one is carbonyl. Now, it gives the lone pair of electron to this, that is sigma. Clear? Now, wait for a moment. That is the ligand donating electron wait friend, give me few seconds so that you can easily understand this thing. Clear? That is the donation. Yes. Now, here the empty orbitals and the back donation also possible. This is pi star and this is pi. So, in metal carbonyl, metal also donate the electrons to carbonyl, that is via back bonding, accepting tendency of ligands. So, in metal carbonyl, donation in both sides. Clear? Due to this reason, there is an involvement of pi, so they are also called pi acid ligands or pi acceptor, my friend. Clear? Whose are pi acceptor? First of one, carbonyl, NO plus, CN minus. Back donation also possible. This is the bonding in metal carbonyl. You can observe here nickel, iron, CrCO6. Clear to you? I think now it is completely visible and you can easily understand the thing. Pi acid ligands or pi acceptor. Am I right, my friend? Yes, sir, you are absolutely right here. Now, donation here, arrow here, now arrow. This is the back donation. Now, I am going to rub this part and we will discuss the next question. Wait for a moment. What is given here? Check it out. The next question is, read the question carefully, what is given here. The answer of this question, my friend. What is meant by Chelating effect? As we know, if there is a ligand, as we know, the formula of ligand may be Ml4, Ml6, suppose. If the ligand attached to metal is polydentate ligand, polydentate, the denticity may be 2, maybe 3, maybe 4, maybe 5, maybe 6. Clear? And if it form a ring around the metal, then this type of effect is known as Chelating effect, and it will increase the stability of the coordination compound. For example, if I take PtCl2En, En is ethane 1,2 diamine. That is the case, my friend. CH2 that is NH2, and here is NH2. Here the donor atom is nitrogen. That is the En, ethane 1,2 diamine. Yes sir. Now it will form the ring structure, have a ability like NH2, CH2, and here is CH2, then NH2, then here, that is clear to you, this is, and here is Cl and Cl. More the tendency of for the formation of ring around the metal atom, more is the ability, more is the stability of the coordination compound, and this effect is known as chelating effect. Lots of example are there. En, oxalate ion, that is DMG, my friend, diene, that is EDTA. These all forms the ring around a metal atom, and it creates the chelating effect, and these are known as chelating ligand. All the polydentate ligand which has a tendency to form the ring around the ring structure around the central metal atom are called chelating ligand, and this effect is called chelating effect. Example is PtCl2En. Clear, my friend? Yes sir. Now I am going to rub this part and we will discuss the next question. Wait for a moment. Now the third one is, what is given here? Read the question. The third question, explain CONH3 Hall 6 3 plus is an inner orbital complex. Yes, whereas NiNH3 Hall 6 2 plus is an outer orbital complex. As we know, do you remember, if the hybridization is D2sp3, then it is inner orbital complex. Yes sir. And we know if there is a presence of strong filled ligand, then there is a possibility of the form, if there is a presence of a strong filled ligand, there is a possibility of the formation of inner orbital complex. Now we here given CONH3 Hall 6 3 plus. As we know, NH3, the donor atom is nitrogen. If the donor atom is nitrogen, carbon or phosphorus, then it is a strong filled ligand, and a strong filled ligand has a tendency to pair up, and that's why it will form the inner orbital complex. For example, here cobalt is in +3 oxidation state. The atomic number of cobalt is 27. It can be written like this: argon 3d7 4s2 is +3 oxidation state. So we will write here argon 3d6, my friend. Am I right? Argon 3d6. Okay sir, definitely you are telling true, because there is a 2 electron from here and 1 electron from here. So the electronic configuration is this one. Now what will happen? This is the case 1 2 3 4 5 1, and this one is 3 1 2 3, that is 3d 4s and 4p, 6 electron 1 2 3 4 5 and 6. Now what is given here? A strong filled ligand, so it will pair up this unpaired electron like this one and this one. And what happened will in this case? Remove this one. Okay sir. So what we observe here, what we get here, there is a 2d, so the electron pair will fill like this: 1 electron pair, 2, then 3, then 4, then 5, then 6. So the hybridization here in this case is D2sp3, my friend. Again I am repeating, the hybridization in this case is D2sp3, and D2sp3 inner orbital complex. Now moving here, Now, if I write here NiNH3, NiNH3 whole 6 2 plus, yes. Look at here again, this one NH3 is a strong filled ligand, yes, a strong filled ligand. That means to say it again has a tendency to form inner orbital complex, clear. But what we observe here, that is the complex is outer orbital, that is hybridization is sp3d2. The hybridization is not d2 sp3. What is the reason behind it? We know that is if there is a strong field ligand, then the hybridization is should be that is d2 sp3. But here the hybridization is sp3d2 because it is, my friend, outer orbital complex. Now the case is what? Why? Okay, I have given you the detailed explanation also. Now nickel is in +2 oxidation state, yes sir. If +2 oxidation state, the electronic configuration is argon 3d8, 4s2 2 electron released. Now what will happen? Like this, 1 2 3 4 5, 4s, that is 4p and 4d, so on, 1 2 3 4 5. This is 3d, 4s, 4p and 4d. Am I right? Yes sir. Now here 1 2 3 4 5 6 7 8, clear. Now NH3 strong field ligand, okay, definitely it will pair up this one like this. If it pairs, only one d orbital is vacant, but we know we need at least 2d orbital, either from 3d or either from 4d. Again I am repeating, either from 3d, either from 4d, because the hybridization would be either sp3d2 or d2sp3, because the coordination number is 6. So due to this reason, a strong field ligand does not pair up this 2 electron, and it use the outermost d. Due to this reason, it forms outer orbital complex like this: 1 pair, 2 pair, 3 pair, 4, 5 and 6. So the hybridization is sp3d2, not d2sp3. This is the case, my friend. What I am telling, sometimes you have exceptions are also there. You have to check out the things. I have given you the detailed explanation of VV theory and how to find the magnetic moment and how to find the hybridization also. And I am going to rub this part. I think you have written this, so I am going to rub it, my friend. Now let us move to the next question, question number 4. Read the question carefully. 3 marks question. Calculate the overall dissociation constant, or calculate the overall complex dissociation if dissociation equilibrium constant for the CuNH3, given that B4 for this complex is 2.1 into 10 to the power 13. Is very simple, that is the 5th one answer. What is given here? B4 stability constant is given here, that is 2.1 into 10 to the power 3, and we know they are reciprocal with each other. Dissociation constant is reciprocal with each other. So what will happen? Dissociation constant will be 1 upon B4. This is a simple explanation. This is the relation. They are reciprocal. Stability constant is reciprocal with the dissociation constant. So the dissociation constant in this case will be 1 upon 2.1 into 10 to the power 13. or you can write here 10 upon 21 into 10 to the power minus 13. After solving, you can get the value. Am I right? Yes, sir, you are absolutely right. Now, what is the second? Cr, I'm moving here. Second one, CrNH3 whole 6 3 plus, okay, is paramagnetic. This is paramagnetic, okay, my friend. And the next one is NiCN whole 4 2 minus is diamagnetic. This is the case, paramagnetic and diamagnetic. Clear? What is the reason behind it? Okay. Now, this is a question. Now, I am writing here. Now, this one NH3 and Cn minus both are strong filled ligand. Yes, sir. Both are strong filled ligand. Okay. That means to say they are forming the inner orbital complex. Let's check. Chromium here, if I talk about this one, chromium here is in +3 oxidation state. Yes, +3 oxidation state. The electronic configuration is argon 3d, general configuration argon 3d, pardon, 3d5 4s1. Now, there is a release of electron take place 3, that is argon 3d3. This is the electronic configuration of chromium 3 plus. Yes. Now, add them, this is like this, 1 2 3 4 5, 3d 4s and 4p, 3d 4s and 4p. Am I right? Yes, sir. Now, put it here, 1 2 3. Okay. Now, NH3 is a strong field ligand, it will try to pair them, but here there is 2 vacant d orbital already present. So, no requirement to pair this one. So, the filling of electron will start from here. That is simple, the hybridization what we get D2sp3. And now look at, there is 3 unpaired electron. Yes, there is 3 unpaired electron, and we know if there is a presence of unpaired electron, then what will happen? The molecule is, the coordination compound is paramagnetic in nature, my friend. Complete explanation related to this question. If anyone asks you how to find the magnetic moment in this case, yes, sir. Magnetic moment mu is equal to root under n plus 2 bm, Bohr magneton, where n is equal to number of unpaired electron. What is the number of unpaired? 3 plus 2 bm. What is 3 plus 2? 5 root 15 bm. Clear to you? This is the case. So, you can easily explain, that is they are what, my friend? That is the paramagnetic in nature. Now, check this one, NiCN4. Okay. Now, NiCN4, what is the oxidation state of nickel? Is Ni2 plus. As we know, the electronic configuration will be argon 3d8, that is, let me check once, CN4, yes. Now, what will happen in this case? Look at, now it has 5, 1 2 3 4 5, clear. Now, this one is S and this one is P, 1 2 3. Am I right? Yes, sir. This is 3D 4S and 4P. 3D 4S and 4P. Now, what will happen? Ni2 plus, and here Cn is 4 times, that is the coordination number is 4. Here the coordination number is 4. Definitely this is a strong field ligand, it will form inner orbital, that is DSP, square planar complex, that is DSP2 hybridization. Yes. Now, as we know, nickel 2 plus, 1 2 3 4 5 6 7 8, this is the case. Now, Cn is a strong field ligand, so it will pair up this electron because it need only 1d, not 2d, my friend. So, what will happen in this case? 1 2 3 4 and 5. Now, put here 1 2, 3, 4. Now like this, clear? Now filling will be like this, one pair electron pair, the next one is 4s, the next one is 4p. Now second pair, third pair and fourth pair, 3d, 4s and 4p, 1d involvement, so hybridization is d, 1s p. Now there is no lone pair of electron. If there is, sorry, no unpaired electron in this case, not no lone pair, unpaired. If there is no unpaired electron, my friend, then what will you say? This one is diamagnetic in nature. Complete explanation related to this question. Am I right? Yes sir. Now check it out. This is the thing. Now I am going to rub this part, my friend, and we'll discuss the next segment. Now the next one is, look at, this is the simple question you can easily solve. Now I am moving here, my friend. This is the, I am talking about the first question. The first one is one, that is the answer of this question. What is given? Listen. Explain with two example each of coordination entity or coordination sphere, the same thing. Coordination entity, or you can say coordination sphere. Am I right? Yes sir. Coordination entity or coordination sphere, that is this one. Suppose if I write here PT NH3 Hal 4 SO4, this is, my friend, coordination entity or the coordination sphere. The bracket in which there is a metal ion and the ligands present, this is known as coordination sphere or coordination entity. What is ligand? Ligand are those substances which contain at least one donor atom which has at least one lone pair of electron. That is the molecule which contain nitrogen, carbon, phosphorus, oxygen, sulfur, etc. That is, they act as a ligand. Ligand are electron pair donor, so they are treated as, my friend, Lewis base. Now there come coordination number. Simple, the number of ligand attached to the central metal atom decide the coordination number. Coordination number, as I told you, is equal to number of ligand attached multiplied denticity. As we know, ligands are monodentate, bidentate, tridentate, tetradentate, hexadentate, heptadentate, pentadentate, so on, my friend. Clear? For example, if I write here PTNS3 Hal 4 2 plus, this is the coordination number is 4 because this is the monodentate ligand. But if I write here PTEN Hal twice 2 plus, now En is bidentate ligand and 2 times, so 2 into 2 4, so it is also a here coordination number is 4. Now coordination polyhedron, as we know, the special arrangement of ligand around the nucleus gives you a particular structure. For example, if I write here Ma4, that is, it may be the structure either like tetrahedral or you can say the octa or square planar. This is the case. This is ligand, 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 metal, ligand here, ligand here, ligand here. Or if the structure is Ma6, that is, it will be the octahedral complexes. This one, ligand, ligand, ligand here, ligand here, ligand. This is the case, my friend. That is polyhedron. Then homoleptic and heterolytic, the type of coordination compound or the type of complexes in which there is a attachment only one type of ligand, like CuNS3 Hal 4 2 plus. This is only one type of ligand attached. So this is the example of homoleptic. But if there is more than one type of ligand, like if I write here PTNS3 Hal 3 Cl 2 plus, or you can say plus minus N. Now this is a now more than one type of ligand, so this is an example of my friend heteroleptic. For example, if I write another example, M, A, B, C, D, 4 different type of ligand heteroleptic. If I write here M, A, B, C, D, E, F, also heteroleptic complexes. Clear, my friend? Yes, sir, definitely. This one is a correct explanation. Now I am going to rub this part and we'll discuss the next one. Wait for a moment. Now the next one, what is given here? The second one is, what is meant by unidentate, bidentate and ambidentate ligand? Unidentate, if the denticity is 1, that is unidentate ligand. For example, F minus, Cl minus, Br minus, NH3, H2O, these are unidentate or monodentate. If the denticity is more than is 2, like En, ethylene diamine, like oxalate ion, these all are the example of bidentate ligand. What is ambidentate ligand? If there is more than one type of donor atom, but at a time only one donor atom donates its electron pair, then they are, my friend, ambidentate ligand. Clear to you? Thiocyanato, isothiocyanato. Clear, my friend? This is the case, ambidentate ligand. Am I right? Yes, sir, you are absolutely right. Now I am going to rub this part and we'll discuss the next question. The next question is, it's very simple. You can, we have done lots of practice on this. So I am leaving this question for you, my friend. Look at, this is hexaamine cobalt 3 chloride. Now this one is alphabetical order A, C, N. So what will happen? Tetraamine chloro nitro, tetraamine chloro or chlorido nitro cobalt 3 chloride, my friend. This is the case. Similarly this one, similarly this one. This one is methylamine. Clear to you? You can easily solve this question. Am I right? Yes, sir. Like TiH2O whole thing. No, I am not going to solve each and every question. It's your turn. You have to solve. This is very simple one. We have done lots of practice on this. Now the next one is, how many geometrical isomers are possible in the following coordination compound? This is the case, my friend. What I am telling, how many geometrical isomers are possible in the following coordination compound? As I told you, there is a rule. Look at, this is Ma3B3. If Ma3B3, the possible combination is 2, that is AA, AB, AA, and BB, my friend. Then AB and AB. That is 2 possible combination. So number of GI is 2, my friend. But they are not optically active, optically inactive in this case. So COCl3NH3 Ma3B3 type. So the number of geometrical isomer is 2. One is face, the second one is mer. Sometimes cis is cis equivalent to face and trans equivalent to mer. Face and mer, facial and meridonian. Now CrS2 C2O4. Here this is MAA3. If the formula is MAA3, now it will not show the geometrical isomer. No GI possible in this case, my friend. Clear? This is the case. No GI is possible. That is the oxalate ion. Am I right? Yes, sir. You are absolutely right here. Now let's move to the next segment, the next question. What is given here? Wait for a moment. Write all the geometrical isomer of PTNS3 and how many of these will show optical activity. I have done this during my lecture also. What is the form is MABCD, my friend. This is the case. Now, what is the possible combination? Yes, sir. ABCD, first combination. Second combination, ACBD. Yes, sir. Now, the next combination is ADBC. Now, three combination. So, number of GI is equal to 3. This is one of the shortest technique to find out. Now, here AB is PTNH3Br. So, in case of PTNH3 Br Cl Py, this is the case. Now, total number of combination. Yes, sir. Combination is, first one is NH3 Br and ClPy, first combination. Yes, sir. The second combination is, tell me, that is NH3 Cl and BrPy. Yes, sir. The third combination is NH3 Py. Yes, sir. Then Br and Cl. Now, combination, that means to say, for example, if I write like this, that is, my friend, square planar, that is PT here. Now, put here NH3, if you put here NH3, so put here Cl, Br, put here Br, opposite each other, perpendicular, like this, and put here Cl, Cl, like here, you can put also here Py and Cl. This is the first one. Similarly, NH3 Cl Br Py. Clear to you? This is the case to write down the how to find the geometrical isomer. Now, how many of these will exhibit optical isomerism, my friend? This is the big case. Generally, in case of ABCD, till now, no optical isomer is isolated. Till now, no optical isomers is completely isolated. Is completely isolated. Still, they say that is the case, only one case, that is, we know, if I write here MA, this one is C, this one is B, and this one is D, there is the possibility of the mirror image formation take place. That is B, that is C, and this one is, my friend, D. That is non-superimposable mirror image. So, we can say by the theory, that is, it can show the optical activity. That is total possible isomer, that is one D form and L form. That is one possibility, that is they can show the optical isomerism. But again I am repeating, till now no optical isomerism is isolated practically. But according to your book, it is given here, there is a possibility. Clear, my friend? This is the complete explanation. Now, I am going to rub this part and we will discuss the next question. Now, the next one is, this is the case, my friend. Discuss the nature of bonding in the following entities. Now, this is the hybridization, basis of valence bond theory. FeCN whole 6,4. Here, Cn is, my friend, a strong field ligand. Okay, a strong field ligand. It is a strong field ligand. Definitely, if there is a strong field ligand and the coordination number here is 6. If the coordination number is 6 and a strong field ligand, then the hybridization will be, my friend, D2sp3, inner orbital complex. Now, iron here is in +2 oxidation state, and what is the electronic configuration will be here, that is Ar3d6. Am I right? Yes, Ar3d6. Now, what will happen, that is the D, this one is S, and this one is P. Okay. Now, 1, 2, 3, 4, 5 and 6. Due to the presence of a strong field ligand, the pairing take place. Now, they will move here. So, what will happen? The filling will be done like this. 1 electron pair, 2, 3, 4, 5, 6. D2sp3, my friend. and no unpaired electron. No unpaired electron. So this one is, my friend, diamagnetic in nature. What I am telling, this one is diamagnetic in nature. Clear? Okay. Am I visible? Good. Now next one. Next one, you can do it. Now do it for me. I am not going to solve each and every question. It's very simple for you. I have discussed lots of problems on this. Fe F6. As we know, F is, my friend, this one is weak filled ligand. This one is weak filled ligand. That is, coordination number here is 6. So we know it will form outer orbital complex, that is sp3d2. Yes, definitely. Here iron is in +3 oxidation state. If it is in +3 oxidation state, what will happen? That is argon 3d5. Clear to you? Because this is Fe3 plus oxidation state. Now what will happen in this case? That is 1, 2, 3, 4, 5. That is 4s. This one is 4p, and second one is 41, 2, 3, 4, 5. Now look at here, 1, 2, 3, 4, 5. Now as we know, this is a weak filled ligand, so it will not pair up this unpaired electron. So the filling will start from here. This one is 4s, 4p and 4d. 1 pair, 2 pair, 3 pair, 4, 1, 2, 3, 4 pair, 5 pair and 6 pair. So hybridization is sp3d2. There is a presence of unpaired electron. So this one is, my friend, paramagnetic. Am I right? Similarly, you can do this one, C2O4, oxygen is a donor atom. If oxygen is a donor atom, we know this is a weak filled ligand. This is also a weak filled ligand, and you can find each and everything related to this. This is the beauty of this chapter. Clear? Yes, sir. Definitely. Now, the next question. Look at here. What is spectrochemical series? As we know, the arrangement of ligand. Suppose if I compare Cn and F minus, as we know, Cn minus has high value of crystal field stabilization energy. The arrangement of ligand according to their CFSE value give rise to a series is known as, my friend, spectrochemical series. Clear to you? Yes. Explain the difference between a weak filled ligand and a strong filled ligand. Weak filled ligand has low value of CFSE. For example, if I write here D4 configuration, clear, and if there is a weak filled ligand, octahedral complexes, if there is a weak filled ligand, so what will happen in this case? The first one, each orbital get 1 electron, T2G3 and Eg. But if there is a strong filled ligand, do you remember crystal field theory? A strong filled ligand. So what will happen in this case? That is, we will write T2G4 then Eg0. First all pairing will take place, then further movement. So this is the difference between weak filled ligand and strong filled ligand. Weak filled ligand, that is maximum number of unpairing here, that is we know we can say high spin complex. Weak filled ligand always form high spin complex, my friend, but strong filled ligand forms, my friend, low spin complex because there is a pairing take place. So in terms of CFSE, weak filled ligand has low value of CFSE, but a strong filled ligand has high value of CFSE, my friend. This is the case, that is weak filled and strong filled ligand. Low value and high value of CFSE. I have taken the example of octahedral complex. Now, what is crystal field splitting energy? What is crystal field splitting energy? As we know, when the D subcell splits due to the presence of ligand 1, 2, 3, 4, 5, that is, it breaks into two parts. First one is T2G and the second one is EG. EG has higher energy and T2G has lower energy. This is the barycenter, and for octahedral complexes this is the case, my friend. Now the energy gap between the T2G and EG is known as, my friend, crystal field splitting energy. For octahedral complex this is delta naught, for tetrahedral complex this is delta T. And what is the relation between delta T? 4/9 delta naught, my friend. Clear to you? This is crystal field splitting energy. Now how does the magnitude of delta naught decide the actual configuration of d orbital in coordination entity? Yes, definitely. Wait for a moment. As we know, if delta naught is greater than pairing energy, this is a two case. If delta naught is less than the P for pairing energy, then what will happen, my friend? If delta naught is greater than the pairing energy, then what will happen? That is, there is a formation of low spin complex, and here if less than, that is, there is a formation of high spin complexes. For example, if delta naught is greater than P and it is a D4 configuration, then what will happen? It can be written like this: T2G greater than T2G4 EG0. But if less than P, it can be written like the T2G3 EG1. First pairing will be done in strong field ligand, that is the low spin complex. Yes sir. And in this case, first one electron, then pairing will be done. This is the case of high spin complexes, my friend. Low spin and high spin complexes. This is the case related to, that is the impact. And low spin complex for a strong field ligand and high spin complex for weak field ligand. And we know a strong field ligand high value of delta naught and weak field ligand has less value of delta naught. This is the complete explanation related to this chapter. I have taken each and every question related to your NCERT books, my friend, and definitely it will help you a lot, my friend. So my friend, time has come, time to say bye bye. Thank you so much.